Okay. Concept we are discussing today is a buffer solution. Buffer solution. So what is a buffer solution? That's the first thing. So buffer solution is a solution which can resist, which can resist change in its pH value, which can resist the change in its pH value when any acid or base is added to it. So I said resist, okay? Resist means it will try to fight it. Usually what happens if you have a solution, let's say we have solution A and its pH is 4. So if you try to add acid in it, let's say we are adding any acid. So what we will see, the pH will go down. And if you try to add base in it, then pH will go up. This is what we see usually. But in this buffer solution, if we add external acid or if we add external base, the pH does not change very much. To say that pH is not changing at all, it will be wrong. pH does change, but pH will not change drastically. But on the same time, if we are having a solution which is not a buffer, and if you're adding any acid or base to it, then pH will change drastically. So all the buffer solution will have a pH range. Let's say there's a buffer, its pH is 7.4. So when this solution will try to protect its pH, let's say we are adding base to it. So if you're adding base to it, then pH will increase. So you may see a marginal change from 7.4, it may go up to 7.6, 7.8, like this, when some amount of base is added to it. Similarly, if you add acid to it, we cannot say that it will not change at all. It will always change, but change will be minimal. Let's say from 7.4, it goes to 7.2 or 7.0. So the point over here is the pH will lie from 7 to 7.8. I'm just taking one example. Okay, this will not be true for all the buffer solution. So pH is ranging from 7 to 7.8 after adding significant amount of acid and significant amount of base. Again, let me mention it. All the buffer has a buffer capacity. So if you are adding up too much base or too much acid, then this buffer solution will not be able to protect its pH. Then it will also change drastically. So after some time, you will see that this pH will, suppose you keep on adding base, and suddenly you will see a jump from 7.8, suppose it directly became 9.0, 10, like this. So after a certain amount, its pH will also increase drastically. Same is true for adding acid also. It can keep on protecting its pH for a certain value of acid added. But if you add too much acid, then again pH will drop suddenly. Let's say from 7.0, this suddenly became 6.0, 5.0, this kind of change you can see. So two things you should be very clear about. Buffer resists change in its pH, but it doesn't matter. It doesn't mean that pH will not change at all. pH will change, but change will be minimal or very small. Second thing which you should be very clear about, it buffer solution doesn't mean that any amount of acid or any amount of base you will add from outside and its pH will not change at all. So every buffer has a buffer capacity. Beyond that capacity, if you are adding acid or base, you will see a sudden jump in its pH. Okay. Now, how does this work and what actually is buffer? I will talk about that part. Anyone want to clarify? If you heard something and you want to re-verify, you can ask me. I just made 2 points here. First point I made, buffer solution resists the change in its pH. Resist means if you're adding base, so usually what happens, pH increases. But for the buffer solution, pH will not increase significantly. Similarly, add acid, pH usually decreases, but for this buffer solution, it will not decrease significantly. pH changes, but changes very minimal. Second point I said, on adding too much acid or on adding too much base, pH will again change drastically. So every buffer has a buffer capacity. Okay, so moving forward, how do we make this kind of solution, which is capable of resisting its pH? How to make buffer solution? So we need to make a solution that should have immunity towards base added from outside, and it should also have immunity towards acid added from outside. Something should be there in the solution which can fight against base. Something should be there in the solution which can fight against acid. So it is very clear now that our solution should have both acid and base. Acid and base both should be there in our buffer solution. So this acid will fight against base added from outside, and the base will fight against acid added from outside. So next question arises over here, that how can acid and base coexist in a solution? Acid will neutralize the base. How can they coexist? So this should be the doubt in your mind. Can anyone tell me any example where you have seen acid and base coexisting in a solution? Anyone? Can acid and base coexist in a solution? No one? Okay. So if you take a weak acid, let's say acetic acid, and you drop it to the water, this will form acetate ion, and along with that we will get hydronium ion. So over here, let's say we are starting with C mole per liter acetic acid. Let's say volume is 1 liter, and we have added C moles of acetic acid. So concentration became C mole per liter. Out of C mole per liter, C alpha got dissociated, and we got C alpha of acetate ion and C alpha of hydronium ion. So C alpha value is very small in comparison to C minus C alpha, because C alpha is negligible in comparison to C. So C minus C alpha is almost C only. Alpha, which is degree of dissociation of this acid, that will be roughly 1% or 2%. Being a weak acid, it does not dissociate enough. It will dissociate 1% or 2%. If it is dissociating 1%, then alpha will be 10 raised to the power minus 2, means 100 times. So C alpha will be C upon 100. So if you see this number will be almost C. So usually the dissociation degree of dissociation of acetic acid, which is a weak acid, comes out to be 1% or even less than that. So this remain almost C, and this value is roughly, let's say, it's coming C by 100, as alpha I have assumed here to be 10 to the power minus 2. This is the equilibrium mixture. So in equilibrium, this acid, acetic acid, and acetate ion, this acetate ion, which is actually a base, let me specify it. This is a base. So we got the desired combination. Now we have acid and base both existing. This is the equilibrium mixture, and both actually exist. But the problem over here will be our base is very less, and acid we have in a significant amount. We got almost C mole per liter, as acid does not got dissociated, but base is very less. So if I call this mixture as a buffer, we can call it, because acid and base both are there, they will try to protect this solution against outside acid or base added. But this solution will be having very small immunity towards acid added from outside. If you're trying to add acid from outside, it will not be able to protect pH. Why? Because amount of base present in this solution is very less. We have very small amount of base to protect against acid added from outside. If you're adding base from outside, then we have enough acid to protect it. We got C mole per liter. Is this thing clear? Do you have you understood why this mixture will not have good immunity towards acid? Hello. Could you guys understand this? Anyone who understood, who have not understood? How many of you understood this?
Sir, can you repeat it again?
I said we got equilibrium mixture of acetic acid and acetate ion, right?
Yes.
When we add acetic acid in water, we get this mixture, correct? But acetic acid is a weak acid, so its degree of dissociation will be roughly 1% or 2%, okay, depending upon. So for easy calculation, I have taken that as a 1%. So if alpha is 1%, means alpha is 1 by 100, correct?
Yes.
If alpha is 1%, then alpha is 10 to the power minus 2. Percentage when you remove, you divide by 100. So C alpha is how much? C alpha will be C by 100 if alpha is 10 to the power minus 2. So C minus C alpha will be C minus C by 100. That means acetic acid will remain almost C. We are subtracting C by 100 from C. So what we will get? We will get almost C, right? We are subtracting 1 upon 100 part from this one. And acetate ion generated is C by 100. So we got here both acetate ion and acetic acid. One is base, one is acid. But over here, this mixture has very poor immunity towards acid because we don't have enough base. Base will protect against acid, acid will protect against base. So we don't have enough acid. Is this thing clear? As acetate ion, how much we have? Only C alpha or only C by 100? How much acid we have? We have good amount, the one what we have added over here. How many of you have not understood? I can repeat again. Please raise your hand. Ask your query. Why you all are quiet? Shall I call name one by one? Okay, Amog, have you understood? Amog, have you understood? Are you there, Amog? If you won't respond, I will remove from meeting. You have to speak. No one will write in chat. Everyone has to speak, okay? Guys, this is a session you have demanded, okay? That's why this is happening. And now if you don't respond, it's not a good thing. Anika, have you understood?
Yes, sir.
Anshul?
Yes, sir.
Okay. Asraj, sorry, Asaj,
Yes, sir, I understood.
Arik, Arik, Arik Paul. Arik Paul, have you understood? No response. Arik, I have to remove you. Dale,
Yes, sir.
okay, just guys keep on responding, okay? So this is just a beginning. So this cannot be a buffer solution because we are not having enough acetate ion. So for the acetate ion, we can look for alternative. We will add acetate ion from different source. This acetic acid will never give us good amount of acetate ion as it is a weak acid and it will be poorly dissociating. So when you look for the sources of acetate ion, any strong electrolyte of acetate ion, so those strong electrolytes are salts. So you can take sodium salt, you can take potassium salt, you can take magnesium salt, whichever you want. Any source of acetate ion we can take. So I have to take a new concentration. So earlier I have called that as a C. So let me write that as a C1. Let's say all the while it was C1. Now for the source of acetate ion, let's say I'm using potassium acetate. So CH3 COOK. And I'm taking C2 concentration of it. So now being a strong electrolyte, this will completely dissociate. We got acetate ion plus K plus ion. This was C2 in the beginning. We got C2 of this and C2 of this. Now in the solution, we have added C2 mole per liter acetate ion. This was the part which was missing. We had enough acid, only the base was lesser. So for the base, I have used another source, potassium acetate, and this source has given us enough amount of acetate also. Now let's see the situation, how this will look like. I will go to different page now. So our equation, acetic acid plus H2O, acetate ion plus hydronium ion. So we started with C1 mole per liter of acetic acid. Then we got C1 minus C1 alpha. This was C1 alpha, this was C1 alpha. Now in parallel, we did one more reaction. We had added potassium acetate, CH3COOK. So that gave us CH3COO minus aqueous plus potassium ion aqueous. So we had taken the C2 concentration of this. So we got C2 concentration of this and C2 concentration of this. So this C2 concentration of acetate ion, this is coming into the solution. So this suddenly became C1 alpha plus C2. Now what you can see here is this acetate ion concentration is now C1 alpha plus C2. So we have added product into the equilibrium mixture. So whenever you add product into the equilibrium mixture, reactions shift to left hand side. So this reaction will now shift to left hand side and this will become C1 alpha plus C2 minus X. This one becomes C1 alpha minus X. This will become C1 minus C1 alpha plus x. So this was time t equal to 0. This was when first time equilibrium was established. C1 minus C1 alpha, C1 alpha, and C1 alpha. Then again equilibrium got disturbed when C2 mole per liter acetate ion came from outside. Then again to re-achieve the equilibrium, reaction got shifted to backside. And again equilibrium got re-established. Now we have to do approximation for the values. And for approximation, I will be drawing some lines. Let's say C1 is this big. This is C1. C1 alpha, as I've shown you earlier, that alpha for acetic acid is like 1% or 2%. So C1 alpha will be 100 times smaller than C1. So this is what we are subtracting. So C1 alpha is, let's say, this much got subtracted, 1 upon 100 of it. And then X got added. How much is X? X is definitely smaller than C1 alpha. That get confirmed over here. Because X is being subtracted in C1 alpha. So X is definitely smaller than C1 alpha. So if I talk about the X here, so X is being added. Something it will go up, which is smaller than C1 alpha. So we are subtracting 1 upon 100 part from C1 and adding even a smaller number than that. So this number will remain almost same. This was C1. This was C1. This was C1 alpha and this was X. So this whole value will remain almost C1. I hope you understood. Now if we talk about this number, so we have added C2 from outside.
Excuse me, sir.
Yes,
Sir,
please.
sorry to interrupt you. I got disconnected in between.
Yes, please.
Could you
Okay.
please explain the slide again?
Which slide? Whole slide?
Sorry, sir.
Sir, you stopped sharing.
Yeah.
Just a second. Can you guys see the screen now?
Yes, sir.
Yes, sir.
So I will just give you a brief of it, okay, whatever I was discussing. So this acetic
Okay, sir.
acid was there, right? It was C1 in the beginning, then C1 minus C1 alpha it became. Usually this is what happened when you add a weak acid. A part of it get dissociated. But part which get dissociated is usually very small because degree of dissociation is very small, like 1% or 2%. So for simpler calculation, in the earlier slide, I was showing you that what if it is 1%? So C1 alpha will be C1 upon 100. So that's why C1 alpha can easily be ignored in comparison to C1. But anyway, I just wrote it. Then acetate ion will be C1 alpha, 1 upon 100 part of acetic acid, and then C1 alpha of hydronium ion. So since if there will not be enough acetate ion, we will not have immunity towards acid. Acetate ion is only source of base inside this solution. So for that, we have added one alternate source, potassium acetate, C2 concentration. So from C2 concentration of potassium acetate, we got C2 moles per liter acetate ion. So acetate ion concentration now became C1 alpha plus C2. We increase the concentration of acetate ion. But the moment you do it, equilibrium get disturbed because you have added product from outside, and that will make the reaction go in backward direction. So C1 alpha plus C2 minus X, let's say X amount will go towards left hand side now. So if acetate ion is getting decreased by X, hydronium will also get decreased by X, and acetic acid will get added by X. So I was approximating the overall concentration of acetic acid, which was C1 minus C1 alpha plus X. So C1 is a big number and C1 alpha is 1 upon 100 or 1 upon 1 upon 90, something like this. It will be very small number in comparison to C1. So if it was only C1 minus C1 alpha, we could easily have written C1. But X is also there. To understand the X, I have told you that X is smaller than C1 alpha. So we don't have to worry about X. As X is being subtracted in C1 alpha, so X must be smaller than C1 alpha also. So this concentration of acetic acid, it can easily be approximated to how much? Anyone? How much we can call it? No one understanding? It can be approximated to C1, right?
Yes, sir.
It was C1 alpha is very small number and X is even smaller than that. So let's say C1 was 100, right? C1 alpha will be like 1 and X will be even smaller than that. Let's say 0.5. So if you 100 minus 1 plus 0.5, how much you get? You get 99.5, right? These kind of things are happening. So C1 alpha is very small in comparison to C1 and X is even smaller than C1 alpha.
Understood, sir.
So now acetate ion, C1 alpha is a very small number, but C2 must be big number because we wanted enough acetate ion. That's why we have added the salt. So we will make sure that enough acetate ion come in solution. So C2 will be a large number. Again, C1 alpha and X are a small number. So acetate ion concentration can be approximated as C2. And we will have some hydronium ion. So these two both number are small, so we cannot approximate. One cannot be neglected with respect to other. Both are a small number. So it will be good if we just write this as hydronium ion concentration. Now this is equilibrium mixture, and this equilibrium mixture is having enough base, which is acetate ion, and enough acid also. So this solution can protect against outside base and outside acid. So this became a buffer solution. What is a buffer solution? Buffer solution will have both component, acidic component and basic component. How do we make it? We can start with a weak acid or weak base. Like right now we are doing with a weak acid. So weak acid will have very poor dissociation. So we can have enough acid in it, but conjugate base concentration will be very poor. So for conjugate base, we have to rely on outside source. So we will import the conjugate base. So for like acetate ion, we could have used any sort of acetate ion, sodium acetate, potassium acetate, magnesium acetate. Over here, I have used potassium acetate. We need to make sure that we are adding enough amount of it because in the solution, we are not having it enough. C1 alpha is very small. So acetate ion we added from outside. Let's say we added C2. So concentration became C1 alpha plus C2. Then when you add the acetate ion from outside, then that will make reaction go backward. This is the Leach-Atliot's principle. When you add product in equilibrium mixture, reaction goes backward. So again, equilibrium will be re-established after reaction goes little bit backward. And then I approximated the equilibrium concentrations. So we get to know that acetic acid concentration is same as it was in the beginning. Acetate ion concentration is mostly what got added from outside, and hydronium ion concentration is unknown. We can find it out. But the silver lining over here is we got enough acetate ion, enough acid. We got enough acid, we got enough base. Both we got here. Now this can be a good buffer. It can protect against outside acid or base added. Let me find out the pH of this solution, then I will show you how does this work, how it can protect the pH. So let me just write the Ka expression of this acid. K of this acid will be acetate ion concentration multiplied with hydronium ion concentration divided by acetic acid concentration. You can take the log on both sides. So log of Ka of acetic acid equal to log of concentration of acetate ion divided by acetic acid plus log of hydronium ion. Now we can take log of hydronium ion on left hand side and log K on right hand side. So both will get negative sign. This will become minus log hydronium ion, which is pH. And log K, when it goes to right hand side, it becomes minus log Ka, which is pKa, plus log of concentration of acetate ion, which I can write as conjugate base, divided by concentration of acid. So conjugate base upon acid. This is the pH. So let's say we have to solve a small question. Before that, if you have any question, please ask me. Then I will discuss 2 or 3 questions based on buffer.
No, sir, no doubts. You can go ahead.
Any other student? Anyone, any doubt, please ask me.
So can H3O plus add as an acid?
Sorry, S3O plus.
So can it act as an acid like in the buffer solution?
Yeah, it is acting as an acid only, right? That's why acetate ion.
So the main acid you took was CH3COH.
The thing is, this hydronium ion is also an acid, but its extent is very less, right? It is already pre-existing. The point here is how it will protect the pH against any acid added from outside.
Okay, sir.
Okay, and hydronium ion is a very good acid. That's the reason this acetate ion is making the reaction go backward. Why we don't have enough acetate ion? Because hydronium ion is giving all the H+2 acetate ion, and acetate ion is converting to acetic acid, right?
Yes.
So this is the situation. Now let's see a few questions on it. If Ka of acetic acid is 2 into 10 raised to the power minus 5, then what will be the pH of 0.1 molar acetic acid and 0.01 molar sodium acetate aqueous solution? So in one solution we have 0.1 molar acetic acid and 0.01 molar sodium acetate. When you see this kind of question, it should click in your mind that this is the buffer question. Why buffer question? Because they taken a weak acid and then its conjugate base, which is acetate ion, it is added as a source from outside. Sodium acetate, for the sodium acetate, 0.01 molar sodium, for the acetate ion, 0.01 molar sodium acetate has been added to make this as a buffer. So you can directly use this formula. I will show you how you can use the formula. This is a small session, okay? So otherwise I could have shown you, or you can come to Lawrence someday. I can teach you that without the formula also how you can solve these questions. So pH equal to pK. What is pK? Negative log of K. Let me solve that separately. pK equal to negative log of K. K is given 2 into 10 to the power minus 5. So that will be minus log 2 minus log 10 raised to the power minus 5. So this became 5 minus log 2. Log 2 is 0.30. So this became 4.7. So pk is 4.7 plus log of concentration of conjugate base. How much will be conjugate base? Conjugate base will be what is coming from this source, sodium acetate. So this sodium acetate will give you 0.01 moles of acetate ion. We have seen this earlier also while deriving the formula that conjugate base concentration will be mostly what comes from outside. Conjugate base already pre-existing in solution will be very less. Like over here, it was C1 alpha and C2 came from outside. So we can directly take the concentration which will come from outside 0.01, which is given here, divided by concentration of acid, which is 0.1. So 0.01 upon 0.1 will be 0.1. And log of 0.1 is log of 10 raised to the power minus 1. So that will be minus 1. So 4.7 minus 1 or 3.7. This is the pH. Ask me if you have any query here. If you have any query, please ask me. No? Okay. Now let's discuss more questions. Little bit of application. Let's see, we have another question. Ka of acetic acid, again I can write 2 into 10 to the power minus 5. This will be given in the question. And we have 0.5 molar acetic acid. And we have 1 molar sodium acetate. So first question will be, what is the pH of this solution? Which you can easily get from formula. Second question will be, what will be new pH if 0.01 molar NaOH aqueous solution is added? So we are adding 0.01 molar NaOH aqueous solution. So let's answer the first part first. So for the first part, pH equal to pKa plus log of conjugate base upon acid. We need to find pK. I have already solved it earlier. It has come 4.7. Plus log of concentration of conjugate base. Conjugate base will come from this source, sodium acetate. So this sodium acetate will give you 1 molar acetate ion and 1 molar sodium ion. So this became 1 divided by 0.5, which is acetic acid concentration. So this will become 2. So 4.7 plus log 2. 4.7 plus log 2 is 0.3. So this became 5. So pH is 5. When we have not added NaOH, the pH is 5. Now what happens when you add NaOH? How much NaOH we are adding? 0.01 molar. 0.01 molar NaOH will generate Na plus ion and OH minus ion. This is 0.01 molar. So this we will get 0.01 molar Na plus ion and 0.01 molar OH minus ion. So once the 0.01 molar OH minus ion came, so this is the base, a strong base, and we already have acid in our mixture, equilibrium mixture. How much we have? I will just write it. Earlier, before adding the NaOH, this is very important, please see it carefully. Before adding the NaOH, acetic acid concentration was 0.5 and acetate ion will be roughly 1. And the hydronium ion, because pH has come 5, so I can write 10 raised to the power minus 5. This was the situation. So this acetic acid was reacting with water and it was generating this. But the moment OH minus ion will come to the solution, acetic acid will not react with water. It was earlier reacting with water. It was losing H plus to water, which was difficult because water is not a good base. Water can act as a base. It has lone pair. It can accept H plus ion. It can offer electron density. But the moment OH minus ion will come in solution, OH minus ion has more electron density. It has 3 lone pair. The moment OH minus ion will come in solution, acetic acid will stop reacting with water and it will react with OH minus ion. Even more stronger base. So with water, it was struggling to react. It was very poor dissociation, but OH minus ion is such a good base, it will take all the H plus acetic acid can give to it. And this will form acetate plus H2O. How much acetic acid we have? 0.5. How much OH minus ion came from NaOH? 0.01. How much will be left? 0.49. This will be gone. Acetate ion were already 1 in the solution. Now 0.01 will be generated. So this will become 1.01. Have you understood the last part? If not, I can repeat. Shall I repeat the last part? Anyone?
So can you repeat it again?
Sure. Last part I'm repeating again. So I say acetic acid is there in the solution, and from outside I have added NaOH. NaOH simply means OH minus ion, which is a very strong base. It can take H plus from anyone with ease because of too much electron density on oxygen. It can easily take out the H plus ion. It can lure the hydrogen with its electron density and it can take it. Acetic acid in the solution we had 0.5. OH minus ion which we have added from outside is 0.01. And in this reaction, OH minus ion will make acetate ion by taking the H plus from acetic acid and plus water. Keep in mind we already had acetate ion in solution. It was 1 molar. Now this reaction, when this will happen, it will happen to completion. We have 0.01 molar OH minus ion, so this is limiting reagent. We have only 0.01, so only 0.01 of acetic acid can be used. So we will be left with 0.49. This will be exhausted, and 0.01 acetate ion will be generated. Let me write this thing if this is confusing you, like this: 0.5 minus 0.01. This has gone, and hydronium ion concentration, which was 10 to the power minus 5 earlier, and now this became 10 to the power minus 5 plus 0.01, which is 10 to the power minus 2.
So no OH minus will be left. Like everything will be here.
Yeah. OH minus ion is a very strong base. It will take H plus from all the acetic acid. Sorry, that was water, okay? It was not hydronium ion. Hydronium ion was 10 to the power minus 5 earlier. Then simply water will be generated 0.01.
Okay.
So you can see here that new concentration of acetic acid is now 0.49, and newer concentration of acetate ion is 1.01. Again, if you apply the pH formula, so pH equal to pK, how much is pK? 4.7 plus log of conjugate base is how much now? It is not 1, it became 1.01. And acetic acid is not 0.5, this is 0.49. So do you think pH will change significantly here? Earlier it was 1 upon 0.5, now this is 1.01 upon 0.49. Numerator increase a little, denominator decrease a little. So this overall value will be little more than 2, right? It is not 2, it will be more than 2. Correct? When it was 1 upon 0.5, this was how much? This was 2, right? Now this value will be slightly more than 2. But it won't be even 3. How much is log 2? Log 2 is 0.3010, so 0.3. Log 3 is how much? 0.47. So this whole value will not be even 0.47. Earlier, how much it was? It was 0.3. So it was 4.7 plus 0.3 earlier. This time it will not be even 0.47 because this ratio will not be even 3. It is slightly more than 2. So log of 2 was 0.30. This time this may become 0.31 or 0.32 if you take the log of this number. Let's say this is 0.32. So how much is the pH now? 5.2. So this is how this solution could protect its pH, correct?
So 5.02.
Sorry, yeah, 5.02. 5.02. It was earlier 5, now it became 5.02. So we added NaOH from outside and pH did not change significantly. This is how the buffer works. Any confusion? Please ask me.
So after adding base also we can apply the same equation, right?
Yeah, we should know the final concentration at equilibrium. Now base got consumed, right? No more NaOH effect is there.
Yes.
Please ask me if you have any confusion. Anyone? Okay, now let me explain to you quickly what is the common ion effect. Okay. For more clarification, please come to Lawrence School. On Sunday, I will be there from 11:30 to 1. You can sit with me. I can explain you more things. try attempting the question on it, buffer solution. If you face any difficulty, please send me personal message or post on DeepL or come to Lawrence. Anyway, I will try to help you out. So we have some more time. Let's discuss the common ion effect. You guys can take the screenshot if you want to, or you could have noted it. Now moving to next slide to explain to you common ion effect. Common ion effect. So let's say we have a weak electrolyte like ammonia. When you add ammonia in water, ammonia take the H plus of water and become ammonium. And along with that, OH minus ion is generated. So if we start with, let's say, C mole per liter ammonia, this will be C minus C alpha. Ammonium will be C alpha and OH minus ion will also be C alpha. So being a weak electrolyte, we will get very small concentration of ammonium ion. C alpha is a small number with respect to C. Ammonia is a weak electrolyte. It has hardly dissociated. But what can make a situation even worse? If you add any strong electrolyte which can generate ammonium or OH minus ion. If you add any strong electrolyte which can generate ammonium or OH minus ion, or any ion which is common with this weak electrolyte. So some strong electrolyte example which has ammonium are the salts of ammonium, like ammonium chloride is a salt. All salts are a strong electrolyte. Ammonium nitrate, ammonium sulfate, any of that. So for example, let's say you are adding ammonium chloride. So this ammonium chloride will generate ammonium ion and chloride ion. Let's say you have taken C2 concentration of this. So you got C2 of ammonium and C2 of chloride. Being a strong electrolyte, it will completely dissociate. So now what will happen? Ammonium ion concentration will suddenly become C alpha plus C2. So you can apply a Leach-Ateliers principle here. When you add product in the equilibrium mixture, reaction goes backward. So C alpha plus C2 minus X, C alpha minus X, and this will become C minus C alpha plus X. So you can see that ammonia, which had hardly dissociated earlier, it gets further suppressed. Its dissociation gets further suppressed if you add any of the ion which is common in the equilibrium mixture from outside. So ions which are generated as a product, if you add any another source of them, which are the strong electrolyte, so that suppress the dissociation of the weak electrolyte. So ammonia, it will dissociate even lesser now. So we have added ammonium from outside. So that means that we have added product in the reaction mixture. On adding product in the reaction mixture, it will make the reaction go left-hand side. So when reaction is going left-hand side, means ammonia, which had hardly dissociated earlier, its dissociation will further be suppressed. And this is called common ion effect. Common ion effect, as a definition, it goes like this. When we add a strong electrolyte with one common ion, to a weak electrolyte, dissociation of weak electrolyte get suppressed. This is what happened here. Ammonia was hardly getting dissociated. Now, when you use another source of ammonium, this will again make the reaction go backward. This is called common ion effect. Common ion effect, which is basically an application of Le-Chatelier's principle. Le-Chatelier's principle says that if you add product in the reaction mix equilibrium mixture, equilibrium will be shifted to left hand side.
So this is different from basic buffer.
Yeah, this is a different example I've taken. I mean, basic buffer. Yeah, this can be the example of basic buffer, correct? But in the basic buffer also, you can see the common ion effect, right?
Oh.
Like earlier case also in the acidic buffer also, you can see the case of common ion. So this one. So we had acetic acid, right? Which was a weak electrolyte that had generated acetate ion. Now when we added acetate ion from different source, potassium acetate. So what has happened? Reaction has gone backward, right?
Because more product is there now.
Extra product got added.
Mm-hmm.
So this is also common ion effect. This common ion effect is simply an application of Le-Chatelier's principle. So when we add any strong electrolyte having a common ion with weak electrolyte in a solution of weak electrolyte, then dissociation of weak electrolyte gets further suppressed. This is called common ion effect.
So the plus X and minus X that we're doing is because of the backward reaction itself, right?
Reaction, yes. It was C1 alpha earlier, then we added C2 from outside. So when product increased, because of acetate ion is common ion in both the reaction. So reaction is going backward. And this is how you can see that dissociation of acetic acid is further getting suppressed. Okay, guys, ask me if you have any query. Otherwise, that's all for today. I will be here and happy to take your doubts for another 5-10 minutes. Otherwise, if you don't have any doubt, please feel free to leave the meeting. This session has been over.
Thank you, sir.
Thank you, sir.
Most welcome. Bye bye.
Thank you, sir.
Thank
Bye.
you, sir. Bye, sir.
Welcome. Bye bye.